Microbiology, MDU University, Rohtak. His area of research is enzyme biotechnology, and specifically he is working on lignolithic enzymes, which are particularly important in paper industry. Okay. He has a lot of good publications and research projects, and today he will be sharing his knowledge upon next-gen sequencing. Okay. So I hope you all will enjoy his lecture. Once again, I welcome Dr. Rajeev.
Thank you, Soni. First of all, I feel honored to be here in front of you, being a part of this training program. I know we are heading towards the completion of this program. I'm sure you guys might have a lot of new techniques, and this might have enriched you for pursuing the coming careers in your lifetime. I hope you must be pursuing research as your career, and I'm happy that you have equipped yourself well with all those basic techniques. Moving ahead, I was going through the protocol book, and I learned that you have done quite a good number of techniques. Although the technique sounds to be basic, but they are very important. I found that you have learned DNA isolation, you have also done chromatographic techniques. You have also been exposed to isolation of plasmids, running and characterizing proteins just through the page. Now, in an instance, it might sound very basic, but let me tell you that all these basic techniques together combine and give rise to a new technology. So all those major technologies which are available today have come from these small basic technologies. Right? To draw a simple analogy, let me give you a very small example. Let me ask you a very common question. Have you ever been exposed, or have you ever got a chance to meet Modi? You never. Have you ever got a chance to shake hands with him? You never. Might be someone might have got a chance to speak to him, but majority of people never got a chance to speak to him, never got a chance to interact with him. But at the same time, it is also true that we have made him Modi. We are the person who have made him an entity which is high up in the politics. Now, the individual importance of you as a small entity cannot be ignored. Had you not voted for this political party as BJP, you might not have become that major entity. So, I'm comparing you with those small techniques, DNA isolation, column chromatography, plasmid isolation, and that has given rise to a big name, that is Modi. So I'm comparing Modi with the next generation sequencing technology, which I am going to discuss today. So this is what I am calling as the next generation. And this analogy which I am trying to draw is that to make you get a feel that this is not a small technique, this is a new technique, and it is not a single technique, it comprises a lot of techniques joined together. At the same time, we shouldn't forget the predecessors techniques, that means the techniques which were prior to the new technique, that is the next generation sequencing techniques. So, to name a few, the next generation sequencing techniques comprises a group of platform technologies which have their own proprietary owners. These are the people who have taken patents over it. So, first of these technologies is the 454 sequencing technology. It is popularly known as 454 sequencing technology. And in books, you will find this technology as pyrosequencing. Okay? And the second technology, which is classified under the next generation sequencing technology, is the bridge amplification, or we call it as Illumina. The name of the company who actually pioneered or has patents over this technology is Illumina, and this technology is based on a platform which uses bridge amplification. There's another technology which is owned by Life Technologies. It's a big name in life sciences. Life Technology is a company which has done a lot of work on next generation sequencing technologies. And the third technology which I'm talking about is owned by the next Life Technologies, and that is called solid sequencing. Moving back to the first, that is pyrosequencing. Yeah, it's important, like before we go on to the next generation, let's also learn about what were the existing technologies before, because the next generation technologies have been built over the previous technologies. So, by comparison to the previous technology is as a switch to make it on. So I said here the next generation sequencing technology is moving, so the previous technologies are all these three. So the popular technologies that you might have studied and are named as Maxim Gilbert, and I would regard them as a Sanger, Fred Sanger, because Maxim Gilbert technology is something which nobody wants to talk more about. And Sanger's is a technology which still holds some potential, and the coming technologies are built upon Sanger's, Fred Sanger. So we won't discuss about Maxim and Gilbert, we'll discuss about Sanger's technology. Now my presentation plan, although this is not, I've added, in the last moments I added one more point, which I'll share with you. So I'll be discussing about the classical methods, that is Maxim Gilbert and Sanger's method. Then I'll take you through, before actually discussing about the technologies, I'll be telling you about what are the potential applications of these technologies, so that you can appreciate the technology. Unless you know the importance of something, you don't give a damn shit to that. So I'll be telling you what are the potential applications, so that you must be knowing that where and when to use these technologies. Then I'll briefly discuss about the Human Genome Project. After that, we will take the three platforms in more detail. So this is done as a simple definition like DNA sequence. Every macromolecule needs to be characterized, and in case of DNA, RNA, or proteins, which are polymeric in nature, the best way to characterize these molecules is through sequencing. And yes, everybody knows that DNA sequence holds the blueprint of our life, what we are, what we will be, and what our next generation is going to be. Everything is, blueprint is there in your DNA. Now, coming to the benefits of sequencing in general. So, first is molecular medicine. Right? The era of the drugs, the chemical medicine is soon going to be over. I won't say that soon going to be over, but there is a new potential therapeutic molecule which is going to come into the play is the biologics, right? So, antibodies can also use as therapeutics. Similarly, nucleic acids can also be used as therapeutics, but these are not drugs. These are not chemicals. So we classify these as biologics. If you just try to remember this term, biologics. So the molecular medicine is a new thing which is coming up, and it is all derived from the sequencing technology. So we all have our own molecular blueprints, and our physiology, phenotype, our metabolism is all governed by that blueprint, which will give rise to the molecular medicine. So we can have improved diagnosis of disease. Diagnosis means every disease manifests itself through certain phenotypic characters, and these phenotypic characters are an outcome of the genetic makeup. If there is a mutation in your gene, your metabolic pathway will be disturbed, so the whole physiology is going to be altered, and that might lead to a disease. Early detection of genetic predisposition to disease. Early detection means, I will give you the example of Huntington's disease. That is not that prevalent in India, but it's highly prevalent in US. So in this disease, this can be diagnosed earlier, before its manifestation. We just need some molecular markers, and molecular markers in this case is a trinucleotide repeat, CAG. If the CAG repeats in your DNA exceeds 25 times, that means you're more likely to be affected by Huntington's disease. So, and similarly, Alzheimer's, and to name a few, even the heart diseases can be diagnosed by your molecular imprint, by your DNA, earlier, right? Before actually you initiate the tendency, or you get a heart attack, or develop a heart syndrome, it can be diagnosed right in your DNA. Similarly, breast cancer, the BRCA1 gene, BRCA1 gene, your tendency to develop a breast cancer can also be diagnosed prior to the onset of the disease. Right? So that's a very important application of DNA sequencing, and this all is done by sequencing your genome. There's a big industry in diagnosis which is just totally based on the sequence and molecular markers, and they are diagnosing the presence of these molecular markers, and they are confirming that, okay, at an early age of 15 or 16, you come to know that you have a tendency to develop a heart disease, or you have a tendency to develop breast cancer. So you can take proper medicines and take proper precautions. Similarly, rational drug design, where should the drug act upon, which gene is responsible for which enzyme, and that particular enzyme is responsible for a particular activity in your cell. So you know where and when to hit if you want to combat a disease. Next is gene therapy. This is something everybody knows. Has been practiced with very limited success, but still, this technique holds a lot of potential. So, gene therapy might give answer to all the genetic diseases which are still prevalent, hemophilia, many other diseases which don't have any molecular or medicinal cure. Pharmacogenomics, custom drugs. One person might be susceptible to a particular disease, but at the same time the other So how do we know? That's through the sequencing of both its DNA and comparing that, okay, this guy is more susceptible, so we can make custom drugs for this particular population or individual. In cancer biology also, you might find a lot of applications associated with sequencing of genes. I told you earlier, cancer susceptibility genes can be characterized or can be raised early in the stage. There could be a risk assessment as well as risk management. Then you can also find out what are the potential points of mutation which leads to cancer. You can also synthesize microRNAs to block triggering of an oncogene. You can also study the epigenetic changes which are responsible for triggering of cancer. Like briefly, I'll tell you what is epigenetics. This is a new line coming up. Epigenetics refers to something. For example, you are inheriting DNA from your parents, but DNA is not the sole thing that is you're inheriting. There is a particular methylation pattern. Okay? We all are humans. We all have similar set of genes, but still we are different. One is due to the polymorphism, SNPs, and the other reasons which are still coming up is that different methylation pattern, which actually regulates the expression of the gene. So the methylation patterns was never given that much attention before, but now slowly the scientists are stressing they're directing their attention towards this, like how does a difference in methylation pattern can lead to alteration in the phenotypic pattern. So that can also be studied through sequencing, then molecular profiling, tumor subtyping, prognosis, therapeutic monitoring, whether or not a drug is working, then prediction of therapeutics response, personalized treatment, and patient stratification. So all this is possible through the NGS, that is the next generation sequencing technology. This is another field, it says bioarchaeology. Archaeology, finding about the ancient, it could be microbes as well as animals or any living form. So bioarchaeology is largely supported by NGS, next generation sequencing technology. We have found dinosaurs, fossils of dinosaurs, but we don't know what was the protein which coded for its strong delta, or what were the ancient form of those genes which might have gone silent in us. So there is always switching on and off of genes. So it is quite possible that the genes which were present in those ancient organisms are now silenced. So we can preserve those genes, we can come to know about those genes, and maybe we can utilize those genes also. Maybe these dinosaurs are more resistant to particular pathogens, or they were much more stronger, better built and all. But still, it's the need of the hour to conserve the germ plasm. You might have read in other subjects also, like in plant sciences also. We are focusing, increased focus is there on the conservation of the germ plasm, so that we can have all sort of genes. We have tall varieties, we have dwarf varieties, we have resistant varieties, we have susceptible varieties. So somehow we can interchange and use these germ plasm for making a new variety. So bioarchaeology is largely now being supported by NGS. Then anthropology, tracing down the evolutionary history, even studying the human migration, that which population migrated from where, and because we have races in human, so it can be a big use. So study evolution through germline mutations in lineages, study migration of different population groups, study mutations on the X chromosome to trace lineage and migration of males, compare breakpoints in the evolution of mutations with ages of population and historical events. Next slide. DNA forensics, something which is now becoming a part of law. There's forensic institute in every state. We have central forensic labs. In Hyderabad, there is a central forensic lab. So most of the high-profile cases are decided upon those labs. So they are all based on DNA sequencing. So identify potential suspects who DNA might match evidence left at crime scenes, exonerate persons wrongly accused of crimes, identify crimes and catastrophic victims, establish paternity and other family relationships, identify endangered and protected species as an aid to wildlife officials, detect bacteria and other organisms that may pollute air, water, soil and food, determine pedigree of seed or trees. So, just to quote an example, the case of N.D. Tiwari was decided by, you are mostly aware of the case of N.D. Tiwari. There was a guy who claimed to be his son. So, it was all proved through the sequencing technologies. In agriculture also, we have disease, insects and drought resistant crops whose genes or DNA can be characterized through sequencing. We can have healthier, more productive disease-resistant farm animals, more nutritious produce, biopesticides, edible vaccines, and many more applications discussed. So, let me at this point of time tell you that the next generation sequencing technology is going to be, or it has already proved its potential in revolutionizing the whole biotechnology. Every lab is now shifted to microarrays and complete sequencing of the DNA and then hitting the gene at the molecular level. So no more people are working on other techniques where, like for example, gene knockout techniques. So all these techniques have gone trivial, and the best way to understand the cellular physiology is the next generation sequencing technology. Now, originally there used to be two methods I already said, Max and Gilbert, which was based on chemical degradation of the DNA. So we have 4 reactions, and we know that this particular piperidine and there are many more chemicals which together cleave the DNA at a specific base, and then running these bases in 4 different wells, we can find that the ladder is built up, and we can decode this ladder. So that was Max and Gilbert. But the Sanger's method, which is still being used in more advanced form, we will discuss that in some detail. So the Sanger's method, also known as the gene termination radioxy method, it has 4 steps. First is the denaturation, primer attachment and extension of bases, termination and gel electrophoresis. So this, no more we are using this technique now. Like the same technique has been advanced. Let me tell you, there were some problems with this. This was quite a lengthy technique. First thing to be done for this technique is you should have your DNA as a single-stranded form. The DNA has to be in single-stranded form. So N13 plasmid was used to obtain the DNA in a single-stranded form. Now, because the fragment has to be cloned. This was a prerequisite for Sanger's method. So we use a primer. This was a reaction mixture. This was a reaction mixture for the Sanger's method, where we used the enzyme, which was the DNA polymerase, then the DNTPs, and the DDNTPs, DNTP, the ATGC, and the dideoxy ATGC. And we need a primer which is just placed adjacent to the MCS. This here is a multiple cloning site where we have inserted this DNA fragment, and just next to the multiple cloning site we have this primer which will amplify the DNA, and at the same time we can come to know will make different reaction products. So the first step is you have to obtain the DNA in denatured form. Second step is annealing of the primer. Third step is extension, and during this extension we are providing the DDNTPs. Here we are providing the DDNTPs, and finally we obtain the result in this form. And the last step was gel electrophoresis. So it's quite an elaborate technique, starting from cloning, denaturing, obtaining the DNA in the single-stranded form, then extension, and then after extension we have, because the DNA will be stopped at different points, as and when the dideoxynucleotide comes, and separating the DNA using gel electrophoresis. This is a form of page, that is a polyclonal electrophoresis. Now, if you look at this structure, this is a DDNTP. If I place a OH here and a OH here, then it becomes a ribose sugar. I repeat, if there is a OH here and a OH here, it becomes a ribose sugar. If I remove this OH, it becomes deoxyribose. If I remove both OH, it becomes a